Soil. It is something we interact with on a day-to-day basis, but what we often don't consider, what a tremendous effect soil has and always has had on our lives, on our existence. And it's because of this constant interaction, think for example about agriculture, how dependent we are on soil, because of this constant interaction, that soil has also become an archive, preserving a large part of our past, a large part of our cultural heritage. Now, when we want to go and investigate this buried past, we find ourselves at the intersection of a number of scientific disciplines, most prominently soil science and archaeology. What these have in common is that they each get confronted with the question, what is present beneath the surface? To solve this question, traditionally, we go and dig and look in the soil what is there to investigate it. But now, alongside digging, we have other techniques that help us look into the soil without intervening it. With sensors, we measure the physical properties of the subsurface so that we can reconstruct what's happening below there. These geophysical techniques you can compare to imaging as it is done in medicine. For example, think about how you study the internal structure of a body with an X-ray. When we look at how these sensors are being used in soil science and archaeology, we see that we are left with a bit of a blind spot. Because in soil science, we look at the soil itself, we study the soil itself, while in archaeology, soil is the box in which we try to detect features and archeological remains with these devices. However, if we want to study the part as an integral as it is, we have to combine these two approaches. And that is what we are trying to do through electromagnetic induction survey. Electromagnetic induction survey is a sensing technique that allows you to look at both the electrical and magnetic variations of the soil. These electrical properties tell you something about the composition of soil, for example, organic matter or clay content, while the magnetic variations tell you something about the mineralogy, and they also are affected by human actions. For example, if you burn something, this would leave a magnetic trace. So, by looking at these properties, we look at different aspects of the soil with one instrument. The instrument itself is made up of a tube in which you have a number of wire coils, transmitters and receivers. Through the transmitter, you send out an electromagnetic signal into the soil responds, and this response is picked up by the receiver coil. And then you can, for the volume you measure, determine these electric and magnetic properties. We then put the sensor behind a quad bike so that we can drive back and forth over terrains, scanning entire areas, looking at the subsurface, sort of like a copy machine goes over a piece of paper. If in such a sensor we combine one transmitter and one receiver, we measure one soil volume. However, when we put multiple receivers in this instrument, we can look at different volumes simultaneously, looking at the electrical and magnetic properties of different soil volumes in 3 dimensions, so to speak. And it is this approach that we used near the now long gone medieval abbey of Boudelot, not too far from Ghent. This abbey was situated on top of a large cover sand ridge, right next to a swampy wetland area, and the abbey itself was fully excavated in the 1980s. When we took our sensor into the wetland area next to the abbey, we found a previously unknown part of this abbey. And here you see one of the electrical data layers that we've collected. You instantly see that there's a lot of variability going on in the subsurface. You see these linear features running through the area resembling ditches and also surrounding 2 smaller areas in the site. And then you see a large-scale variation that coincides with this wet soil environment in which we find ourselves. Now, we already have a lot of information about this site, but our knowledge vastly increases when we look at the magnetic component of our signal. Because then we see that in these two small enclosed areas, you have large magnetic traces that seem to resemble building structures erected amidst this wet environment. Now, in a following step, we, based on these results, conducted excavations to evaluate and add more information, sort of an archeological keyhole survey, if you want, to get more insight in what we're actually looking at. And this keyhole surgery confirmed what we saw in our data. We indeed have these ditch systems that are dug through the area that we see in the electrical part of our signal, and we have these large brick foundations showing up in the magnetic component of our signal that were used as a foundation to support larger, probably wooden buildings. In the following step, we then combined all of these different data layers from the sensor, these different soil volumes, with the knowledge of the excavation data. And by doing this, we were able to reconstruct this environment in 3 dimensions. And what you see here is the result of this procedure. You see the ditch systems again, but now we also see embankments next to those ditch systems, adding to the drainage of the site. You see that it's a low-lying area with only a couple of high-lying zones that now are prominently located in the landscape, and on top of which we have our building structures. In a nutshell, we have a full view of how humans have adapted this landscape and have occupied it, and how this reality is still present beneath the surface. An approach that has a large potential, as you see, also in different environments and different periods, ranging from the Middle Ages, as we have in Baudelot, all the way back to prehistory, from near Ghent to, for example, Stonehenge in England, where everybody knows the Standing Stone monument, but this is only a small part of a vast prehistoric environment buried beneath the surface. However, when we're studying here, we have to keep in mind that this area is still being used today. And it also was used in the 1980s when there were a number of music festivals there. And any of you who's already been to a music festival knows that when you leave the camping grounds, a lot of rubbish is left behind. Bottle caps, drinking containers and stuff like that. And when we go there with sensing equipment, then we obviously measure those things as well. When we look at one of the electrical data layers over here, we see that there's a lot going on, but our vision is blurred by this snow screen of small anomalies from the left-behind litter of the festival. But then, by using again these different soil volumes we have, we can take out these metal particles to actually go and see at the things we're interested in. And the effect of this gets obvious once we start looking at the archaeology in this site. Here you have 2 prehistoric monuments that we see in the magnetic part of our signal, the original data, and then through this procedure we can go and peel off the present to look more at the archaeology that we're actually interested in. So you see that this approach, this use of these different signals, offers also a technological advance. But it is more than just that. Through combining soil science and archaeology with electromagnetic induction survey, we can scan our way into the soil, starting from the present all the way down, offering a new perspective on our buried past.